Can you hear me? Great. Okay, so thanks for inviting me to speak today, Matt. As you mentioned, it's a little bit of a different topic than the other talks today, but going to talk about how we exploited a bug in the Chrome Sandbox in the browser process to escape the Chrome Sandbox. So first, a little bit of background on me. My name is Tim Becker. My handle online is usually TJ Becker, sometimes with an underscore, as is the case on Twitter. And I'm a security researcher at Theory, who's currently focused on browser exploitation, as you, I guess, could guess based on the title of the talk. But I'm also an avid CTF player. If you're unfamiliar with CTFs, they're capture the flag competitions. They're a form of hacking competition. It's actually how I got my start in security, by playing these competitions in high school. And then I later joined PPP. And I attribute most of what I know about security to playing CTFs. So if you haven't ever tried them, I recommend giving it a shot. But we're not here to talk about CTFs. We're here to talk about Chrome. So on the agenda for today is first a bit of background about Chrome. So a little bit about the security architecture and the IPC mechanisms in Chrome. And that should be enough to describe the details of the bug and explain how it can be triggered. And then we'll get into the details of how the bug was exploited. And there's a little bit of a different approach that we use than typical sandbox escape bugs that have been publicly disclosed. So you might find that interesting. And then at the end, there will be some higher level takeaways. So if you didn't especially care for the nitty gritty details of the exploit, hopefully there's still something interesting at the end that you might take away. So Chrome's philosophy for security is slightly different than the other major browsers. Chrome doesn't implement a whole lot of exploit mitigation strategies, and instead relies much more heavily on strong sandboxing. So most of the interesting attack surface on the web, such as DOM rendering or script execution or anything media or graphics related, typically runs in a sandbox process. And in fact, Chrome actually is, I think, the only major browser implementing site isolation, which is a policy that keeps data from distinct origins in separate sandbox processes. Meaning that if a user visits a malicious website that compromises their browser or compromises one of these sandbox processes, there's not very much that a malicious attacker could do, because data from other origins, such as Google or Facebook or Twitter, should be protected and not accessible from that sandbox process. But obviously not all of Chrome can run unsandboxed, otherwise it couldn't really do anything like web-related or access the file system or anything. So there is one central process called the browser process, which runs completely unsandboxed. And this is kind of the main process whenever Chrome is launched. And some of the other sandbox processes have varying degrees of sandboxing with access to different parts of the system, but the browser process is usually the one being targeted in a sandbox escape exploit because it's completely unsandboxed. And so this means that if an attacker wants to fully exploit Chrome, it typically requires 2 or more bugs. So first, they have to get code execution within one of the sandbox processes. And that usually requires 1 or more bugs. And then from there, they have to try to escape the sandbox. And again, this usually requires 1 or more bugs. And the sandbox escape, especially lately, is usually the bottleneck here, because Chrome designs their security architecture so that even if the sandbox processes get compromised, the attacker's ability should still be very limited, and they have pretty strong security boundaries to prevent sandbox escapes. And so this talk is going to describe one bug in the browser process that a compromised renderer process, which is kind of like one of these processes that is responsible for rendering the DOM and script execution. One of these renderer processes can use this bug to get code execution in the browser process and therefore escape the sandbox. Okay, a little bit about Chrome IPC. So all of these different sandbox processes are running and they need to communicate with one another. So the primary IPC mechanism used in Chrome is called Mojo. This is kind of a newer mechanism or IPC platform, and the legacy IPC platform is kind of entirely phased out, almost entirely phased out. And so it's not going to be relevant for this talk, but I just wanted to mention it for good measure. Mojo is a platform agnostic implementation of like most of everything you would want to do IPC. And the way that it works is you specify your messages that you want to be able to send across process boundaries in a Mojo IDL format. And then during Chrome compilation, code for each of your target languages that you are going to use in Chrome to communicate over this Mojo interface will be generated, and you can link against it in all your various languages. So here's an example of that. This is an example Mojo interface. It's actually the one that we're going to target, but I'll describe a little bit more about what its purpose is later. For now, just take away that you write this interface definition. Here it defines one method called filter installed apps. And during compilation, some bindings get produced for all the various languages. For instance, C++, Java, if it's an Android Chrome build, and JavaScript. And these various bindings basically implement the interface in that corresponding language, that if you were to implement this interface, you should provide all of these methods and whatnot. And then it also implements proxy objects. So if, for instance, like if from C++ you want to use an instance of an installed app provider in a remote process, you would use this proxy object to send and receive messages. So if you notice, one of the target languages is JavaScript. And this means that there's actually support for speaking over Mojo in JavaScript. And there's a Blink flag, which Blink is kind of like the rendering engine in Chrome for enabling Mojo.js, which allows a web page script running in a web page context to directly talk over Mojo. And so, of course, this feature is not enabled by default for security reasons. However, a compromised renderer can actually enable this feature without needing to escape the sandbox by just flipping the appropriate bit in memory and then starting a new JavaScript context. What this means for the purposes of writing a sandbox escape exploit is that you can essentially assume Mojo.js is enabled, and it's kind of more or less equivalent to having a compromised renderer process if you just enable this command line flag. It's not exactly the same because you don't have, read-write, arbitrary read-write access or anything in the renderer with this, but most bugs that you're going to target for a sandbox escape just require speaking over Mojo. Okay, so a little bit more background on Chrome before I can describe the bug. So every frame on a web page, which is the main frame or any iframes that are included, are backed by a render frame host object in the browser process. And this is kind of the main point of communication for each frame over IPC. And many of the Mojo interfaces that a renderer would want to acquire access to implement any of the web platform features, it'll get a handle to it by asking the render frame host to create it for it. And so this code snippet here runs during initialization of a new render frame host. And it basically populates a map for all the different interfaces that it can provide, and then it gives a callback to invoke whenever a renderer requests that interface. And in this case, the callback simply just creates a new C++ implementation object implementing this interface and hooks up the Mojo handle connection to that implementation. Okay, so that should be enough to describe the bug. First, a little bit of background on the bug and its lifetime. So for those that haven't heard, Edge browser is now Chromium based as of January this year. And so the Edge developers are kind of working on a Chromium fork at the moment. And some of the features they're implementing are getting merged back into Chrome. So this installed app provider interface that I showed you was originally only implemented on Android. And it was a feature, it was part of the web platform feature to allow a website basically to check if the corresponding native app is installed on the device. And I guess Microsoft wanted a similar feature, or I guess the same feature, to be implemented on Windows in Edge, so a website could check if a native app is installed. And so the Edge team implemented this interface separately in C++. So the Android version was written in Java. And so from a memory safety standpoint, it was probably secure. But this version was written in C++, as is most of desktop Chrome. And as I mentioned, some of these features are getting merged back into Chrome. And so this one actually did. And it landed in Chrome 81, which was released sometime in March, I believe. But it was behind an experimental flag because this is a new experimental feature that they were trying out. And the implementation had a use after free vulnerability in it. But the interesting thing was that this bug was actually reachable even with the flag disabled, because where they actually checked if this feature was enabled was just after the bug could be triggered. And so a little bit later, the code was refactored a little bit, and the bug still existed, but it happened to be moved behind this experimental flag. But I guess this is one interesting takeaway is that because Chrome is on this like 6-week release cycle, the reachable version of the bug was in Chrome 81, which should live for about 6 weeks before Chrome 82 comes out. And so this bug would have been exploitable in the wild for about 6 weeks. But we found it and reported it just before Chrome 81 hit stable. So thankfully it was fixed and it never got pushed out to users. So what actually is the bug? So this installed app provider impl is the C++ implementation of this interface I described. And recall that it's created by the render frame host whenever a certain frame in a web page requests access to it. And so this object actually stores a pointer to this render frame host object. And this is a raw pointer. It's not a smart pointer of any kind that is able to detect if this render frame object has been destroyed. And in the implementation of this filter installed apps function that this interface provides, it uses the pointer to look up the corresponding render process and check if it's an incognito tab. Basically, it's a process level feature, whether or not the web pages being rendered in it are incognito or not. And the problem is that this render frame host can be freed from the renderer. So for instance, if the render frame host corresponds to an iframe on the web page, if the web page removes that iframe, it causes the render frame host to be freed. And furthermore, this installed app provider impl isn't freed whenever the render frame host is freed. It actually stays alive as long as the Mojo connection to it is kept open. This means that if a web page is able to free this render frame host before calling the filter installed apps, this render frame host pointer will be stale and a use after free should occur. Okay, so now I'll describe how we can actually trigger this bug. I alluded to it earlier, but here's the exact procedure. So a web page can create a new render frame host by adding an iframe. And then in this iframe, in that corresponding JavaScript context, you can use Mojo.js, which can be enabled by this compromised renderer process, to request a handle to this installed app provider. And then we free the render frame host from the parent frame by deleting this iframe. So the issue that we face whenever we were trying to trigger this bug is that when you delete the iframe, all of the JavaScript objects in that frame's context get deleted. And that includes the Mojo handle. And if you recall, we need to keep the Mojo connection open in order for the use after free to be triggerable. So we found one way to keep this connection open, which is basically to take the Mojo handle from the child frame and pass it up to the parent frame. And there are a few ways to do this, but we used one of the Mojo.js features called Mojo Interface Interceptor. So then from the parent frame, we have this Mojo handle now pointing to this installed app provider for a freed subframe. And now we can simply call the filter installed apps method, and a use after free should occur. So here's actually what that looks like in JavaScript. So in the parent frame, we run this first function, which triggers the bug. So as I alluded to on the previous slide, first we allocate a subframe, and then we set up this Mojo interface interceptor so that we can basically receive the Mojo handle that we want from the child frame whenever it has it prepared for us. And then whenever we get this handle from the child process, we set up a proxy object to the installed app provider so that we can invoke the appropriate method. And then we free the subframe. And once it's freed, we can invoke the method, and a use after free should occur. So then the code for the child frame is very simple. All it needs to do is create a Mojo message pipe to be able to send messages. And then it sends a message to the render frame host requesting access to the installed app provider. And it hooks that up to one end of the Mojo pipe. And with the other end, it sends it to the parent frame, which will later be used in the parent frame to set up the proxy object. Okay, so that's how the bug can be triggered. Now I'm going to describe how we exploited it. So whenever you're exploiting a use after free like this, it's often useful to replace the freed object with controlled data. And actually, in the Chrome browser process, this is relatively easy because there's very little allocator hardening, which would prevent like objects of different types from reclaiming the same memory. So it's also really easy to control allocations in the browser, where you can make an allocation of any size and put any data there using the blobs API, which is just kind of a web platform feature that lets you store arbitrary data blobs in like a browsing session. And furthermore, the render frame host is a huge object. It's one of the biggest like C++ objects in Chrome, which means that this freed pointer is in a very rarely used heap bucket. So unless we're like creating another frame or something, it's very unlikely that this freed heap region is going to be reused by anything else. So if we just allocate a very large blob of the same size as the render frame host, it's extremely likely that it's going to replace that freed object. And now we have controlled data there. And so as we discovered while exploiting this, it's usually just the first blob we allocate replaces the render frame host. But for stability, we usually do a few more just to be sure. Okay, so this render frame host object has a bunch of pointers that it expects to have within it. And the problem is that with perfect ASLR, there's no valid values that we could put for those pointers that would prevent a crash, let alone do anything useful. But our Sandbox escape was targeting Windows, recall, because this is a Windows feature. And Windows actually has a pretty significant ASLR weakness for the sort of local privilege escalation scenario, which is that base addresses of images, meaning DLLs or executables, is only randomized once per boot. So this means that like if the same DLL is loaded in multiple binaries on Windows or in multiple processes in Windows, it should have the same base address. And conveniently, Chrome.dll is a massive 400 megabyte DLL, which is loaded in all of the Chrome processes. And so this means that if we're assuming we have a compromised renderer process, we should be able to acquire this chrome.dll base address, and it should be the same in the browser process. So we actually do know a little bit of the memory layout of the browser process, at least where certain DLLs are loaded. And so if you recall the buggy line of code, it's a virtual function call on this render frame host object. So yeah, it takes the pointer and it calls get process. And if you know how virtual function calls work in C++, the object has a vtable pointer within it that points to a table of functions that can be invoked if it's a virtual function call. And so if we have some code that we want to jump to in like control flow hijack this get process call, there needs to be a pointer to it at a known address so that we can point the vtable pointer to that code pointer. And unfortunately, we don't really know the address of any controlled data, so we can't kind of build arbitrary like code pointers at a known address. But the previous slide tells us that we do know where chrome.dll is loaded. And all of the virtual function tables in Chrome are stored in this DLL. So this means that we're able to call any virtual function on any object defined in Chrome with our controlled render frame host object. So unfortunately, this doesn't seem like it's enough to get arbitrary code execution yet, because it's very unlikely that there's just a virtual function in Chrome that we can just sort of redirect this call to that will give us code execution. So we'll have to build some stronger primitives out of this. And typically to do that, we'll want to exploit the bug multiple times or trigger the bug multiple times in different ways to sort of manipulate the Chrome process into doing something more useful. But there's a slight problem with that in this case, which is that the result of this virtual function call to get process is used to make another virtual call called get browser context. And then that result is used to make yet another virtual function call. And so if we just point get process at some virtual function, we'd have to make sure that it's returning sort of a process object or some object that meets the constraints that will prevent those future calls from crashing. And that is extremely limiting. But fortunately, we found a nice way around this, which was to instead point get process to some virtual function that just returns like the address of a class member or a reference to a class member, which in machine code just takes the this pointer and adds a small offset to it, so that it's returning a pointer into data that we still control, because we have this massive blob that is replaced the render frame host. And so get process will, or whatever we redirect get process to, will return a pointer that still points into our controlled data. And then get browser process is another, or sorry, get browser context is another virtual call. And so we're in the same scenario as we were with get process. And so we can once again do redirect it to this virtual function that returns a small offset ahead. And finally, we have the third virtual call, which we fully control. And now it can return any value. So we truly can redirect this to any virtual call, and the process shouldn't crash. And whatever the result of this final virtual call is, shouldn't affect the stability of the Chrome process. So here's a diagram that summarizes everything I've said so far about the exploit. So we have our blob that has replaced the freed render frame host object. And within it, we're putting these vtable pointers into the chrome.dll, which is, we're able to know the base address of it based on leaking it from the renderer process. So in chrome.dll is all of the code implementing Chrome, as well as the data, and that includes the virtual function tables. So we take our first vtable pointer and we point it at this virtual function. There's many of them, but we choose one that returns a pointer which is 8 bytes ahead of the first one, which is exactly one word, one pointer. And so we can repeat the same thing for the second virtual call. And then the third call, we can point at some different vtable, which invokes some different target function. And that target function will run whenever we trigger the use after free. So now we can start to build more powerful primitives. And we'd like to be able to jump to arbitrary code. That's usually a useful exploitation primitive. So to do that, we want to be able to build a fake code pointer and put it at a known address. And the problem is that most of the data that we can control in the Chrome browser process is in the heap. So to do that, we need to get a heap pointer. And so it's actually really easy to do, given what we have so far. We can just use a target function, which is a virtual function that does some new allocation and stores it into a class member. Because what this will actually do is place that pointer into our blob, because our blob has replaced the freed render frame host object. And then because it's a blob, we can ask the browser process at any point in time to send the data back to us, because blobs is just kind of like a generic data store. And so we can read the blob data back, and within it should be the heap pointer of that new allocation. So then from here, there's one sort of common path used to escape the sandbox. So now that we have a heap pointer, we can spray code pointers into the heap and then point the vtable at it and have like arbitrary control flow hijack. So one thing that's commonly done is to jump to a stack pivot gadget, which puts the stack pointer into one of our controlled blobs in the heap. And then you can use return-oriented programming to execute arbitrary code. But we actually used a slightly different approach that, for this bug at least, was a lot cleaner and easier to achieve. So what we decided to do instead was disable the sandbox. So remember that we're already assuming that this bug is being used in a chain where we can compromise a renderer process at will. And so if we create a renderer process which is running unsandboxed, then the other part of this bug change is going to execute code outside the sandbox if we can get that to occur. So in order to get Chrome to run unsandboxed, you can pass this command line flag --no sandbox. And this flag is propagated from the main browser process to all the child processes, which implement most of the sandboxing. And so if this flag is passed to a child process, it basically skips setting up the sandbox. And so if we were able to just kind of append the sandbox flag to the browser process at runtime, it should get propagated to the child process, and then these new renderer processes, which we're able to exploit, will be running outside the sandbox. So thankfully, this is actually really easy to do. There's a function in Chrome called set command line flags for sandbox type, which takes a command line flag object, which is just kind of a parsed version of the command line string passed to Chrome. And it takes a sandbox type, which is just a C++ enum, so just small integer values. And if we can call this function with the browser process's command line object and pass the appropriate integer for no sandbox, then it will append this switch to the object. And so then any process that's created will run on sandbox after this point. And one other benefit of this approach, beyond just the fact that it's a little easier than ROP, is that it's a slightly more platform independent, because ROP payloads usually have to be tuned to a significant degree to the platform you're trying to exploit. But this approach works kind of the same on all platforms, provided you can get the offsets out of the Chrome binary easily. So we think it has some benefits. Yeah, so unfortunately, that function that we want to call, we have to control the arguments for it. And also, it's a non-virtual function, so we can't just use our virtual function sort of gadgets to invoke it. So we want to call this function with controlled arguments. And there's actually a convenient object in Chrome which already does this. It's a Chrome callback object. It essentially just stores a function pointer with some, some bound arguments. So there are many, many virtual functions in Chrome which invoke these callbacks, which are stored. And there's many virtual functions that sort of have this callback object waiting to be called whenever the virtual function runs. And the approach that we took here is to invoke one of these virtual functions and control the function pointer and the arguments for the callback, and basically point it at that command line flag function with the appropriate object and enum. And that's basically it for the exploit. So some takeaways are that because Edge is now Chromium based, the Edge developers are working with basically a relatively new code base to them. And so some common pitfalls that might occur in Chrome programming might be reemerging just simply because it's a newer code base to the developers. And interestingly, some of these bugs will not just affect Edge, but will actually get merged back into Chrome. Another big takeaway is that exploiting browser process bugs to escape the sandbox can probably be done entirely in JavaScript now. So you likely don't need to write your sandbox escape component in native code and run it in a compromised renderer process. Also, an ASLR weakness in Windows is one of the key things that made this single bug exploitable. Otherwise we probably would have needed a second bug, which would give us some sort of information leak from the browser process. And in fact, macOS and iOS both have a similar ASLR weakness. So this bug would have likely been exploitable on macOS as well. However, it seems to me then that Linux and Android have the strongest ASLR when it comes to this local privilege escalation scenario. And so exploiting Chromeboxes or sandbox escapes on Chrome on Android is probably currently the hardest target when it comes to ASLR, at least. And for us, disabling the sandbox was a much cleaner and more adaptable approach than getting arbitrary code execution in the browser process. So with that, I think I have time for some questions. And if you want to see all the details, there's a nice blog post on our website at theory.io. Thank you.
Thanks, Tim. Yeah, definitely the blog post. Nice is an understatement. Like, it was very well written with the nice graphs, and it was like the other like good blog posts I see that are like that good, and in terms of like well written and everything, is like Project Zero. They also have like some pretty good blog posts. So, but the slides were pretty awesome too. Reminder, by the way, don't forget to send me your slides, or you can make a pull request directly. Okay. That's pretty cool. So what did you say, like Linux and Android the strongest? Because you said like Windows had some ASLR like weaknesses, and something on Mac OS, but not on Linux, Android.
Yeah, that's right. As far as I'm aware, there's no equivalent weakness on Linux, and therefore not on Android either. And so for this local privilege escalation scenario where you already have code running in one process and you want to exploit another process on the same machine, Linux and Android seem to have the strongest ASLR in that scenario.
And question from Jaziel. I might have missed it, but how long did it take to find the bug? How long did it take to exploit?
Yeah, so finding the bug, it didn't take too long actually, because this is a variant of previous bugs that had been reported. And so using the Chrome code search tool, I was just able to basically look for similar code patterns, and this was one of the results. So I don't know, probably a few days of understanding that bug report and then looking for variants of it. was enough to find it. And then writing the exploit took probably about a week or two. I think I took some breaks in between whenever I would hit a wall, like the ASLR situation or trying to avoid a crash and whatnot. So on and off, I'd say about a week or two.
That's pretty good actually. And I don't. You didn't mention it, so I don't know if you used it in that scenario. But I would be also interested to hear your thoughts. What do you think about CodeQL? Did you try to make a script on like a query on CodeQL to find that bug? Did you play with it a bit, or like could that be helpful? I'm just asking because I started to look at it like yesterday. I was like, oh, that's quite cool actually, because you can do like data tenting, all those things. Like, oh, I've been
Yeah.
living under a rock. Where was I when this thing was released?
Yeah, no, great question. I actually didn't use it to find this bug, but I have since been learning it and am trying to apply that using CodeQL to find other bugs with slightly different code patterns. So yeah, it's a great thought, and I think it's a promising technology.
Yeah, because I would assume here the Chrome Sandbox is open source, right? Because I think with CodeQL we need to recompile something to create like a CodeQL database and all those things.
Yep, that's right. There's actually a great blog post. I forget the author's name, but he found a few Sandbox escapes using CodeQL, and he actually open sourced the queries he used, as well as gave a brief description of how he built the CodeQL database for Chrome. It's on GitHub somewhere, so if I can find the link, I'll include it somewhere.
Yeah, definitely. And also like for the GitHub, when you make your pull request, there is a readme.md, so feel free to add in your reference link to it.
Sure.
Jaziel is like, oh, switch at my next question. But yeah, like I do agree. It's quite it's quite promising because, well, although you said like that bug, like it took you only, although like I don't think you're like a good benchmark for that, but you say it took you like a few days to find it, right?
For that particular variant, yeah. I mean, so I
Yeah.
have been looking for bugs in Chrome for quite a while before that, but
Okay, okay, that makes sense.
learning the code base and getting familiar with it. But that particular bug variant I was looking for, yeah, that only took a few days because it was just a few hundred results in the Chrome code search tool.
And how many engines are using Chromium now? So you said like two obviously is Chrome and Edge. So, but they're not using it yet. They're planning to.
No, actually,
They are,
the
right?
latest releases of Edge are Chromium based,
Okay.
and as far as I'm aware, this bug was in Edge as well.
Okay, got it.
Yeah.
And yeah, I guess like for Edge, it's a bit more tricky with like like Windows Defender, Application Guard, and all those things. Like the Sandbox is probably. I mean, I guess like you would have to like. Well, I guess not everyone is using Windows Application Defender Guard, but Application Guard. Did you look at the Edge variant yet, just for fun, or to compare like the exploitation, or?
No, actually, I haven't tried exploiting it in Edge. I haven't looked into Edge too much yet
Okay.
as an independent project. I know that the the parts of Edge that are built on top of Chromium aren't exactly open source. The latest I've checked, they're
Mm.
uh, last I checked, like the open source release for it actually just had compiled object files for all the things that Edge adds to base Chromium. Um, so it's a little more tedious to research, but I'm planning to look at it in the future.
Yeah, like that would be also like quite interesting because I mean, for application guard, I think now it's an option only in enterprise version of Windows, so it's not very like mainstream. So I don't think you would need to like bypass it. But I
Mhm.
think they're expanding the usage to like Microsoft Office now, and I would not be surprised if, like by next year or in 2 years, it would be like a by default feature. To be honest, at that point,
Yeah.
uh, which would be like quite cool. But then you would need like some some like Hyper-V like box, to escape. That would be like pretty crazy.
Yeah.
Um, cool. do we have any more questions from the chat? I well, don't think so. Well, thanks for your time, Tim, and for like joining us tonight. Well, I guess this morning. Yeah, you're in Texas, right?
No, I'm actually in Wisconsin, but same time
Okay,
zone.
okay. Yeah,
Yeah.
yeah. Cool. Well, it was very interesting. I'm definitely gonna rewatch it. It was pretty cool.
Yeah.
Thanks again,
Thank you.
Tim.
Thanks for inviting me.
Hi guys. So that's it. We're approaching. Well, we're not even approaching. This is the end. You know, like Jaziel, you missed all the opportunities to ask more like interesting questions. But although like we can still continue to discuss it on the Discord after. And if you guys haven't joined, definitely join the Discord so you can watch Jaziel's progress with CodeQL and get the daily report. And I said it, but you know, like, don't forget to subscribe. It's easier to get notifications, so I don't need to send emails. And yeah, so if you have any feedback for today's edition, do not hesitate. Like, you can send me a DM on Twitter or just like a message on Discord. And yeah, thanks for watching. I hope you enjoyed it. So the presentation slides should be up either like tonight, right after this, or tomorrow. So they're gonna be on GitHub. The link is in the description of this stream. So if you just check the YouTube description, you're gonna see like the description. If you want to watch the previous edition of well, Opcode live stream, they are on YouTube also, so that's quite also convenient. And usually we also tweak, you know, when we have some live issues where like there's too much noise in the background, or if there is like some any technical issues, like we fix it after, and we upload like a cleaner version on YouTube. But today, like I don't know, luckily we didn't have any issues, and as usual, you know, like because it's live, and like you know, Dragos was asking me like if I was like alone. Yes, I'm doing that alone here. So whenever there is no issue, I'm quite content with that. I'm like, oh wow, you know, and every time it's still a bit stressful. But feedback is welcome. If you have any recommendation, suggestion, if there is any good blog posts that you have seen, because the format, and I think it's gonna stay like this for a while, because that's already the 5th edition. You know, 1 edition every 2 weeks. Something, you know, like 3-4 like talks, you know, or an average of 30 minutes for each of them. And yeah, that's pretty much it. So if you see even any good blog posts, or even if you do have, because I know a lot of the people watching are usually quite technical too. If you have a good blog post that you want to talk about, definitely let me know. It does not need to be exclusive, as long as it's very interesting. And there's so many like content online to read now that it's pretty hard to track. So my reading schedule now is basically to invite people to discuss about whatever stuff they wrote about, so I can learn at the same time, rather than just trying to go like straight into reading it and getting all the details, you know. So far, that's pretty much how I'm managing my reading list. And as an audience, I also encourage you to do the same thing. So if there's cool stuff that you have seen, don't hesitate to share the link. And if there's like themes you want to talk about, definitely. So we have few presentations for the next edition, but the CFP is always open. If you just go on the website, anyone can submit. And yeah, so thanks again, everyone, and have a nice evening or a nice day wherever you're from. Thank you.